Hey everybody, I want to do a second part of three parts, or a second video of thrri videos for chi-square hypothesis testing. So I want to talk about the more complicated version of chi-square hypothesis testing, which it says one thing in this worksheet because this is for a different class. When I was presenting this slightly differently, not a different class, the same class, I just taught it differently. So yeah, let me explain what we're going to do. So what we're going to do is we're going to test to see if two categorical variables are related to each other or not. So in other words, if one affects the other one. And the way we're going to do that is a little bit complicated. It's going to involve counting observations in each category and seeing if they're approximately the same for all the different variables. And I'll show you what I mean. It's called the chi-square test of association. That's what I want to call it. It's going to say independence here and then homogeneity down here. They're actually the same test, pretty much. Do I have one down here? It's down here somewhere. Yeah, here's a homogeneity one. So I'm just going to explain how they work, and that's going to take some doing. And then I'll show you how to do it on the calculator. I'm not going to do one of these by hand because it is terrible. Like it'd be a lot of work to do this by hand, and I'm just not gonna do that. I mean, I guess it's not. So the last one we did had 4 categories, right? In the goodness of fit section. Here we would have what is this, 20? And then the way you calculate expected is also a hassle if you're doing it by hand. So it'd be a lot. But luckily, doing a bunch of calculations is what calculators and computers are really good at, and they're already set up to do this test, so that's what we're going to do. So let me explain what the idea here is. So here's like, let's say I wanted to determine if age and gender, the one variable that I'm calling age and gender, so like adults and kids, and then females and males, whether age and or gender affects someone's favorite ice cream type, or someone's favorite form of eating ice cream, whether they like it in a cup cone, sundae sandwich, or other, which bowl, I don't know. There's probably some other ways that you could have ice cream. And we're going to see if those two things are related, the variable age, gender. So in other words, whether you're adult or child, and male or female, and what form you like your ice cream delivered in, essentially. Bucket? I don't know. Anyway, we're going to see if those two things are related. So here's how we're going to do this. The basic idea goes something like this. If it was the case, all right, I'm actually going to start by writing the hypotheses, because I want you to see what the null hypothesis is, so that we can use that to build our expected value, our expected counts, because that's what, that's where the expectations come from, is because we start by assuming that the null hypothesis is true. So the null hypothesis for a test of association goes something like this. The null hypothesis is that the two variables, aren't related. I guess related isn't the word I want. I want associated. This is where you get that test of association. And then, of course, the alternative hypothesis is that they are. HA, the variables are associated. And when I say associated, maybe correlated is a better way to say that. In other words, one affects the other one. You could also say that the two variables are independent is the null hypothesis, and dependent is the alternative hypothesis. Those things all mean the same thing. So the reason I wanted to show you this is because we're going to use this idea of the variables not affecting each other to figure out what our expected counts would be, which is going to take a little bit of explaining. I got the hiccups a little bit here. So let me go here. So here's the idea. If it was the case that neither age nor gender, so in other words, whether you're a woman, man, girl, or boy, that you would expect all of those categories of the variable age gender to have the same favorite ice cream types. Or rather, you would expect the distribution of favorite ice cream type to be approximately the same across those 4 categories of the variable. So here's the idea. We have taken a different amount or a different sample size for each category. So we're viewing this essentially as a stratified sample, right? I like people over here, and I'm stratifying them into these 4 groups, right? Male and female, and adult or child, right? All those combinations. And so for the women, we surveyed 131 women, and we got this distribution of favorite ice cream types in our sample. That should be, well, if the null hypothesis is true, that should be approximately the same distribution that we would see for men, because whether you are a man or a woman is, according to our null hypothesis, does not affect what your favorite ice cream type is. Same thing for girls and boys, right? We would expect the same distribution here and the same distribution here. Each of those things that I described, like this right here, is called a conditional distribution. So I need to talk about what marginal distributions and conditional distributions are first. So marginal distribution of one particular variable is just the percentage falling into that category, or the percentage falling into each category. It's exactly the same thing. If you think back way to the beginning of the course as relative frequency. That's all marginal distribution is it's the relative frequency in each category. So the marginal distribution of favorite ice cream type is 107 out of 547 for cup, and 109 out of 547 for cone, and 151 out of 547 for sundae, right? So you can see that right here, right? This right here is a marginal distribution. So the marginal distribution of favorite ice cream type. You can do exactly the same thing for the marginal distribution of age and gender, right? It'd be 131 out of 547, whatever that decimal is for women, and 105 out of 547 for men, et cetera, et cetera. Okay, so here's the idea. If it is the case that all of these strata have the same distribution of favorite ice cream type, if that's true for the population, right? It's not true in the sample, obviously. But if it is true in the population, then the proportion I would expect to be in any one category, so in any one cell, would be the marginal distribution, right? If I'm thinking of, maybe let me back up a second. If it is true that all 4 of these strata have the same population marginal distribution of favorite ice cream type, then the best estimate of that is this, right? Rather than just looking at the women, I would like to compare the women to the overall distribution and see if it's significantly different than that. That's the basic idea here. So what we're going to do is say, okay, well, if it is true that women, men, girls, and boys all have approximately the same population marginal distribution of favorite ice cream type, then this is the best, well, this here is the best estimate we can get of that from our sample, right? So what I want to do is say, okay, well, if it is true that the population is approximately, the population preference for ice cream in a cup is 107 out of 547, well, that's my expected percentage for the women. And it's also my expected percentage for the men and the girls and the boys, right? It's the same expected percentage for everybody because it's the overall expected percentage for the population. If all the populations are, or if all of the strata have the same population distribution. If they don't, we'll see some differences, right? We'll get more women who like their ice cream in a sundae, or more girls who like their ice cream in a sandwich, or whatever, right? Some of the expected counts will be different than what we would expect if they all matched this distribution here. So that's the idea. We're going to calculate the percentage we would expect, which is the number in the category of cup divided by the total, right? So that's the percentage. We're expecting 19.6% of everybody to like their ice cream in a cup. And then we say, well, okay, well, we surveyed 131 women, so I would expect 19.6% of these 131 women to prefer their ice cream in a cup. And I would expect 19.6% of the 105 men to prefer their ice cream in a cup. I would expect 19.6% of these 141 girls to prefer their ice cream in a cup, et cetera, et cetera. You do that for all of those categories, right? So you do, and that's how you calculate the expectations, is this number here divided by that number gives you the expected percentage for the population overall. And you multiply that by this number, which is the population in any given stratum. Stratum is the singular of strata, which is plural. Okay. And then here, I'm gonna post this. It's gonna be a little bit, or I'll link this in Canvas. It's gonna be a little bit, I would say archaic, but it's not exactly the way I'm going to explain this, but this is the basic idea here, right? So 42 out of 131 is 0.321. I don't want to say this percentage. So here's what I'm getting at here. This right here is the conditional distribution of favorite ice cream type given age and gender, right? So within any age and or gender strata, so within one strata here, I find the marginal distribution, I find the marginal distribution of favorite ice cream type within just the women. And the same thing, I find the marginal distribution of favorite ice cream type within just the men and the girls and the boys, right? All separately. So here is how we're going to do our test. So this right here is me explaining all of that stuff I just said. So feel free to look it over. It'll give you a chance to think about it. Like, you can rewatch the video and you can read the text that I wrote. So here's the idea. We're going to do this. This is going to be our hypotheses. Now, we're not actually going to write them as the variables are independent. Here we're going to say favorite ice cream type and age and gender are independent, and favorite ice cream type and age and gender are dependent, or associated and unassociated is the way I'm going to say it here, right? So I'm not really going to say the variables. You never want to do that, because that is just the general form of the hypothesis. It's not specific to the test that you're doing. So the test we're actually going to do says null hypothesis, age, gender, and favorite ice cream type. Oh, that's not the word I wanted. Favorite. Are independent, or are not associated, is the way I'm going to say it. Aren't associated. And of course, the alternative hypothesis is they are associated. I'm just going to say they are. They are. I hope they is clear enough here. There's a lot of right ways to say that. They are correlated. There is a correlation between age, gender, and favorite ice cream type, et cetera, et cetera, et cetera. Okay. Here's how we're actually going to do this. So I'm going to use the calculator, because as you can imagine, that whole process that I just described of going through and calculating the expected number of, say, women who like their ice cream in a cup by doing 107 out of 547 to get the percentage, and then multiplying that by 131, that gets you E. And then you have to calculate observed minus expected squared divided by expected. So we'd have to do that expectation calculation for all 20 cells. And then we'd have to do the chi-square contribution calculation for all 20 of the cells. And as you can imagine, that is super tedious and also very likely to go wrong at some point, right? It's unlikely you're going to be able to do that calculation completely perfectly if you do it all by hand. Luckily, we have a calculator. And so here's how we're going to do that. Now, first thing I need to introduce is the concept of a matrix. So a matrix has a lot of, it's got a lot of meanings. Matrices are really neat. They're very, very useful in math. We're not going to do any of that with any of the normal matrix stuff with matrices. What we are going to do instead is use them as a table. So this is the way your calculator takes in a table. And you can see it's just a table, basically. This matrix is 3 by 5 because it has 3 rows and 5 columns, and that will be relevant to us when we try to make one. So let's go to the calculator and do that. Why are you doing this to me? What? It's open. It's right here. Yeah, bam. I knew it. Okay, so here is how you put a matrix into your calculator. There's a matrix button, matrix. So I'm going to go here. Now this has three different menus, right? There's names, which is not the one we want right now. Math, which we are not going to use at all, I think. I think we're never going to use math. And then edit, which is how you edit a matrix. So when you need to tell the calculator, I want you to use matrix A, that's what names is for. When you need to change what is in matrix A, that's what edit is for. And so that's what we're going to do right now. So I'm going to go to matrix A, and it says, so here's why we need to know what size it is, right? So the matrix we want, let's go look at our table, that one. All right, so our table right here. So what I'm going to do is I'm just going to put in the table, right? Like that's the goal here. We're not going to have any headers. This calculator doesn't understand headers, but that's what I want to put in, not the totals. Your calculator will do the totals for you. So this is 4 rows by 5 columns. So I want to do a 4 by 5 matrix. It's here. So let's go back to the calculator. So I want this matrix to be 4 by 5, 4 rows by 5 columns. You can see it's got the right size. So I'm just going to type in all the observed counts. So that's going to take me a minute to do. So let's see here. Whoop. Okay. So women, 42, 30, 25, 23, 11. I'm not sure I can remember that. 42, 30, 25. All right. I tell you what I'm going to do. Just to avoid a bunch of dead air here, I'm going to go ahead and type these in off camera and then show you a little bit how I did it. I'll be right back. All right, I'm going to show you me typing in the last row into the calculator, just because it might be helpful to know how to get around your matrix. So I haven't quite finished yet. You can see I've done the first 3 rows. So let's do the last row. So I've got this is boys, so 15, 27, 60. So I'm you can see what's highlighted here. So 15, then I'm gonna hit enter to move to the right, and 27, enter, 60, enter. You can also move around with the arrow keys. You can move around in your matrix with the arrow keys. I forgot what the last 2 numbers were. Let's go back and look. We've got 54, 14. 54, 14. Okay. So you can see that I've got this, am I sharing the right thing? I don't remember. Man, okay, great. I've got the matrix typed in here, and all I did was fill in this into the calculator. You might ask yourself, can we just do this in Sheets or in Excel? And the answer is, unfortunately, not, as far as I know. You'd have to do it manually. They'll do goodness of fit tests, at least Sheets will. But I don't know how to get it to do test of association, which is annoying because these are the ones you really want to do on the calculator. Anyway, so I've typed this into the calculator. So let me show you what we're going to do with that now. All right, so I've got this matrix here. I'm going to go ahead and quit. The matrix is still in there, I promise. So we'll go back and look. So second matrix. You can see that matrix A is 4 by 5, exactly like we just put it in as. So I'm going to quit out of this. And then what I'm going to do for the test is I'm going to go to stat, tests, chi-square test. So goodness of GOF test is goodness of fit. That's the one we covered in the previous video. This is the one we're doing right now. And it has 2 things which look kind of the same. One says observed, the other one says expected. And you might be thinking to yourself, I have to go put in all the expected counts? That sounds like a pain in the neck. And it would be, but you don't. This, despite the poor design here, this is two different things that they're saying. This is, where did you put, this is the calculator talking to, where did you put the observed counts, and where would you like me to put the expected counts? So observed is where you put it in the table, like we just did. Expected is going to, whatever's in there is going to get deleted. Whatever's in matrix B is going to get deleted, and the expected counts are all going to get calculated for you, which is great because that makes things a lot easier. So let's go to calculate. And that's actually all you have to do. You put it in the table and you hit calculate. And there we go. We got a chi-square of 61.6 with a p-value of something very, very tiny, right? 1.15 times 10 to the negative 8. So this is really small. That makes us want to reject our null hypothesis and think that the two variables are related to each other, right? Remember, that's not the right thing. Our null hypothesis was that age, gender, and favorite ice cream type are not associated. They are independent, is the null hypothesis. And we think that's not true. We think they are associated with each other and that they are not independent, that they're dependent, that favorite ice cream type depends on whether you are an adult or a child, and or whether you are male or female. That's our conclusion. So let's go write a conclusion here. Yeah, let's do this text-wise. Our conclusion. This evidence or this data suggests that age, gender. Let me see. I'm going to say that favorite ice cream type is depends on a person's age and or gender. There's my conclusion. That looks like a perfectly good conclusion. Okay. So that's how you do the basic test of association. Notice I had a really tiny p-value. So we rejected the null hypothesis. So let's go back here for a second. Where is my, yeah. I want to talk about the degrees of freedom very briefly. You might notice that they were not, well, the degrees of freedom for a goodness of fit test were just number of categories minus 1. And you might say to yourself, well, we have categories in 2 different variables. How do we figure out the degrees of freedom here? So it's 12 in this case, and I'll show you why. It's 12 because our table, I have to scroll back up to the table here, is 4 by 5. So this right here is our table. So we've got 4 categories in one variable and 5 in the other. So what we wanted, so the way you calculate the degrees of freedom is you subtract 1 from each of those things and multiply. So 3 categories are free, with 1 being determined once you've got the 3 that are free. And then 4 categories here are free, with 1 being determined once you have the 4 that are free. And that leaves you 12 total free cells in your table, which is where you get the degrees of freedom. These things can vary. So the reason we say these things can vary, by the way, is like, here's the basic idea. If we know what the total is, and we know any 3 of the, or any 4 of these things, then we can figure, I wish Word wouldn't do that. Then we can figure out the 5th one just by subtracting. So in other words, given the total, 4 things are independent, and then the last one is determined once the other 4 are chosen. So that means that since we're assuming that we know all the totals for degrees of freedom calculations, that we have these things are all free, because you can have 3 free choices and then one choice that's been determined if we know the total here, and 4 free choices and 1 that's been determined once we know the total here. So that gives you 3 by 4. So 12. That's how you calculate degrees of freedom. So it's rows minus 1 times columns minus 1 is the basic calculation. Let's see here. So this is just me showing you how to do the what am I trying to say here? How to do this test in the calculator. And you'll see that indeed we got the same thing here that we got when we did, which just means that I typed in everything right, basically. Okay, so that's how you do the test. Notice we got to our p-value. That's what we wanted for the test. Remember that I said that the way we stratified our sample, we really have kind of a double stratification here, where we've got sort of two variables, right? Age and gender. And so the natural question might be, what am I trying to say here? Natural question might be, is it age or is it gender that's affecting people's favorite ice cream delivery method? Is it, which one is it? And so the way we might try to break this down in categories is make an age table and a gender table. And so here's what I mean by that. Let me share up the calculator here. If I do one just for adults, I could do the following. I'm going to make a matrix. I'm going to use C and D. So matrix C is going to be just, oh, gosh darn it, I do that all the time. That's what happens when you do names, by the way, is it just says use matrix C here. So I'm going to go to edit and C. And so here's what I'm going to do. I'm going to have 2 rows this time with 5 categories. And those 2 rows are going to be for adults and children, right? So this is going to be a 2x5 matrix. And I'm going to put all the adults into the top row and all the children into the bottom row. So let's go look at my table for a second. This table right here. So for the adults, I'm going to combine men and women, right? So I'm going to have 73 in for cup and 59 in for cone, etc. So I'm going to go ahead and do that right now. I'm going to pause the recording so you don't have to sit here and watch me add and type, and I will be right back. All right, I've got the table typed in. Let's go look at it. Where did my calculator go? Is it here? Okay. Weird, it wasn't showing up on Zoom. So here's what the table looks like when I combine them, right? So I just added up men and women here, added up boys and girls here. That's what I did. And then I'm just going to do another chi-square test of association. You didn't see any of that because I didn't share my screen. Let's try that again. Sorry. I think I'd be good at this by now. So I've got, I added up men and women here, boys and girls here. And so I'm just going to run another chi-square test of association on this. And see if there is, there's a difference between adults and children, right? See if those are the strata that matter, or maybe it's gender or the strata that matter, or maybe it's some combination. But yeah, so let's just go ahead and run that test. So stat tests, chi-square tests, and here I put that one in C. I kept A and B as the original table. So I want to use C and D here for these. So the way I get the calculator to use C and D is now I'm gonna have to go back to matrix, and now I want these, right? So I put that into C. So that's where I put observed, and I would like expected to be put into D. So go to matrix, under names, we'll go D, and we will calculate that up. And oh, this p-value is even smaller. It makes me want to reject the null hypothesis even more. So it seems like there is a difference between adults and children. And you can run the same thing for males versus females, right? You get the girls and the women in one category and the men and the boys in one category, and you do the same exact thing. You do the same thing I just did. If you go and do that yourself, I will give you a tip. Or I'll just tell you the answer is that those are not, you don't detect an association there. If you do like men and boys and women and girls, like you don't get a difference between those two, but you do with the adults and the kids. So that's a way you can break down your strata a little bit. All right, so is that the last thing I want to do? I want to show you. Yes, so there is sort of another kind of test of association, but not really. So let me explain it to you, and then I'll explain why I don't really consider it different. So it's called test of homogeneity. Like this one up here is called the test of independence, because you are testing to see if two categorical variables are independent or dependent, right? And we determined that favorite ice cream type and age gender was dependent, like that there was a dependent relationship there, that that favorite ice cream type depended on what category of age gender someone fell into, right? That different distributions for the different strata. Homogeneity is exactly the same thing, thought of in a slightly different way. So here is what homogeneity test is. It is testing to see if two different populations are homogeneous, which is to say the same, with respect to a particular categorical variable. So here I've got, after the fun cheerfulness of ice cream, we've gotta bring it down a little bit with alcohol versus no alcohol and severity of injuries in car accidents. So here's the idea. I've got a category, severity of injuries, that I'm thinking of. Why are these are oddly placed? Sorry. That I'm thinking of as, what am I trying to say here? Gosh darn it. My mouse is not working like I wanted. That I'm thinking of as two different populations of, in this case, car accidents, right? Those that involve alcohol and those that don't. And I want to see if their distribution of injury severity is the same or not. Now you might notice that that's essentially what we just did up above with favorite ice cream type. We just considered these two different strata within the same population. Then it would be an independence test. But if we're thinking of them as two different populations, then it's technically called a homogeneity test. However, the math is 100% the same. It's literally not different in any way. That's why when we go look in the calculator, they don't have independence and homogeneity separate. They just have something called chi-square test, because it's the same test for both of them. It's test of association. So you do it literally exactly the same way. And I think it is a little too pedantic to make a big deal of the distinction between the two. And so I'm not going to bother. I'm just like, if you're trying to determine if two categorical variables are associated or not, if they're correlated with each other, then you just do a chi-square test of association. Don't worry about whether it's homogeneity or independence. The difference is mostly semantic. It can affect the way you gather data, but we're not going to worry about it too much. Yeah, so you just do literally the exact same test to get you do exactly the same test and you get the same result. It's literally just another example of the same thing. So I'm not gonna go ahead and do this one. You can jam it into your calculator. You get something that looks like this, right? Tiny p-value, big chi-square value, and you'll end up rejecting the null hypothesis and concluding that the presence of alcohol has an effect on the severity of injuries in a crash. There you go. Okay, I'm gonna go ahead and this here, yeah, we have one more kind of hypothesis test that I want to teach you called the test of single variance, which is entirely different than these than the ones that I was just talking about. So I want to put it in its own video. So I'll go ahead, stop that video here, and I will see you guys in the next one.